What is incremental programming? It's a style of programming where you do stepwise programming, so you submit small snippets of code and you get immediate feedback on this code. And this is useful to test new constructs, for example, libraries or algorithms, and to do rapid prototyping of exploratory programming. And incremental programming, we see that in redevelop print loops or, for example, in Jupyter notebooks. In previous work, they found the class of sequential languages, and in the paper they state that sequential languages naturally occur in REPLs. And the main idea of a sequential language is that we have two programs in the language and we can compose them into a new program. So in this example we have P1 and P2. We can compose those into the composition, and the interpretation of P1 then P2 is the same as the interpretation of the composition. So this diagram commutes. So if we have composition following these criteria, then we get incrementality for free. So our goal is to compose languages without losing flexibility while promoting reusability. So what do we have to do for that? We want to compose language constructs and the semantics of these language constructs. This is basically a reformulation of the expression problem, and for that we use datatypes a la carte. Then we want to promote reusability and compatibility of our operators, and for that we use Funcons as a lingua franca. So what this means is that all our operators, they basically translate to the same semantic domain. And this makes it easy to compose the different operators together. Otherwise, we have to translate between different semantic domains, and that gets messy. So as a solution to that, we use Funcons. And we build on top of that a layer in which we can modify the structure of a language via our composition. What I mean with that, I will tell in a bit, but first some background. What is datatypes a la carte? It's a method introduced by Wouter Swierstra in 2008, and it allows you to define data types and operations on these data types in isolation. And it does that by implementing data types as functors. So here we are working with languages, so our data types are language constructs. And in the example, I have two language constructs, a number and addition, and these are implemented as isolated functors. So they have no relation whatsoever. And then what we can do is we can compose these data types by taking the co-product of these functors. And after that, we can tie the recursive knot by taking the fixed point of our co-product. What this means is that we can use these constructs in the argument itself. So the fixed point passes the fixed point to our operator, and what this means is that this argument will be passed to our addition, and that means we can use addition inside addition. So we can use recursive addition. That means tying the recursive knot. Now that we have our data types, we can just add a new data type if we want. So if we want subtraction, we would just define data sub, which is also a functor, and then we can add this to our composition, and this way we can build up more complex composition of data types without modifying our existing definitions, which is a nice property. And then to assign behavior to these data types, we write algebras. And algebras are of the type FA to A, and what this does, it extracts our component into a certain semantic domain, which is our A. So in this case, I have an example algebra named eval, and eval translates our functor into an integer. So in the case of num, we translate it to num, so this is f of A, and this is our A, and in case of add, we translate it to addition. And that's what an algebra does. And because datatypes a la carte is built on initial algebra semantics, by initiality, we get a free fold over our data types. And this is a catamorphism. And that is encoded here, which is a fold over our data types. And what this means is that it doesn't matter which data types we have, as long as they follow these conditions, we can fold over them and translate them to our semantic domain. Now that we have that, what are funcons? Funcons is a component-based approach towards formal dynamic semantics. And what they do here is they define semantics of programming language constructs in they define the semantics of programming language constructs in a formal way, and they can generate micro-interpreters for these. And these micro-interpreters we can compose, and then we get full interpreters for our language. And here we have an example of how this looks. So these maroon-colored constructs are funcons, and here we encode the application of the function to the result of integer add. So this is basically calling integer add 12 on the value stored in the variable f. And then we apply that to do function application. And there are many different functions for different language constructs. And these are also defined in isolation. And we can compose them to create actual executable interpreters. And now, with this, we want to build a layer on top of this in which we can support incremental language definition via composition by delaying language structure choices. And what do I mean with language structure choices? Well, we might define the simple Lambda calculus using the three constructs. We have variables, abstraction, and application. And in the constructors of these constructs, we already make a decision. So in this case, we decide that we have a type expression, and these constructs belong to that type. We also make the choice that our abstraction, the body of our abstraction, is also expression. So in this case, we already decided that nested functions are allowed in the language. But not all languages have nested functions. So to support languages without nested functions, we would need to introduce a new type, new constructs, etc. So our solution to that is to split it up. Instead of having one constructor definition, we split it up in operator declarations. These define our operators, var, apps, and app in our case. And operator declarations have arguments, which we call operands. And these all have a unique name. So for example, in the case of abstraction, we have an operand called var and an operand called body. And to make these unique, we prefix them with the name of the operand. Operators also have an arity, which is just a number of arguments. So now we have this, and now to define the structure of a language, we use sort constraints. And what these do is they assign one or multiple operators, so that are these things, to sorts. And this can be to an operand, so we can assign variables to the body of abstractions. So this is a sort, the operand is a sort, or we can use auxiliary sorts. Auxiliary sorts are sorts that do not occur as operands, but we can just use them as a way to reduce boilerplate. So here we are back to our original example where we had the expressions. So we assign our operators to the expression, and then we use a subsort constraint where we distribute the expression over our operands that we want to target. But these two definitions are isolated from each other. So the operator engineer defines the operators, and the language engineer defines the constraints, and this way the structure. So if we don't want nested functions, we can just remove apps from expression, and we don't have nested functions. We don't need to introduce new operators or anything. So we don't have to do that. And then to define the semantics of these operators, we write translation functions, which are just translating our operators into a specific semantic domain. And in our case, that's Funcons, which I introduced earlier. So here we see how the Lambda calculus is implemented in our system. And the main thing that's important here is that when we translate our operator, our operands, so in this case x and b, are already translated to the semantic domain from the usage of the catamorphisms. So this way we don't have any influence on the children of our terms, which ensures there is some consistency in the definition someone gave to an operator. However, the existing semantics is not always enough for every language, because you can't envision all usages. So what we can do is we can specialize operators by adding wrapper Funcon terms. So in this case, we want to extend our abstractions, turning them into procedures, so that we can have return statements that do an early return. To do that, we introduce a new operator called return. It has one operand, the value we want to return, and the semantics is just a simple return. And then we say, okay, I want to add return to the body of abstractions, and when return is part of the body of abstractions, I want to translate the semantics of our body in the abstraction to wrap it in a handle return. And what this does is this catches the effect of returning and then returns the value returned. So here we modify the definition of apps without actually changing the operator definition. So we have here here our operator definition of apps, which is like this. And now by associating glue code, we add a handle return around the B. But we don't have to modify our existing definition, which is nice. And with all this, we come to the following language definition, where a language is a structure. We have a set of operators. We have a set of top-level operators. These determine the entry points in our language. And from this, we can generate a parser. Then we have a family of sets representing the operator assignments. We have the semantic functions. We have glue functions. And we also have initialization functions. These go over the top-level operators, and they allow you to modify the semantics of your language according to your usage. So if you use a language in a REPL, you probably want to handle uncalled exceptions differently than if you run it in production. And with initialization code, you can modify that without having to do a lot of work. Then to test this system, we went for an implementation in Haskell, mostly because it was less work and we could have some properties checked without doing a lot of type checking. So we use some template Haskell, which I will introduce in a bit, but to define our operators, we use GADTs. So an operator is defined as follows, where we have the universe, which contains all our operators, and we have a meta type of our operator. Then what we do is we check if certain parts are belonging to a certain sort. So here we check if the type T, which is used here, that is our second argument, that is the app's body, if it belongs to the app's body type class. And this is how our sort constraints are checked at compile time. And then the return is our GADT with the type set to the meta type of the operator. So every operator has a meta type, and then we assign these meta types to type families, and this way we can check these constraints at compile time. So sorts and the meta types are just empty data types. We just use this at the type level. It has no runtime information. And the sorts, which we saw with the app's body, the operands, they're implemented as type families. And then we can do a template Haskell call. So every time you see a $, it means we do template Haskell. This means this is done at compile time and it generates Haskell code. And then to assign an operator to a sort, we say gen sort constraint, where we have the meta type of the operator and we have the sort. So this is simply the encoding of Haskell of our assignment of the apps operator to the app's body. And to handle auxiliary sorts, we introduce another type family, and then we can do again a sort constraint where we assign our meta type to our sort, and then we do a gen subsort which distributes the elements of our auxiliary sort to the target of this call. And this is the encoding of the following expressions in our model. Then to handle semantics, we use type classes, and this is mostly inherited from datatypes a la carte, where for every operator we have an instance of the two Funcons type class. This translates an operator into our semantic domain, which is relatively straightforward. These are functions that generate Funcon terms. And the most problematic part here is that we are not actually working with functors, we are working with higher order functors. So to ensure that our kinds are correct, we need to wrap certain parts with this K constructor, which is a constant functor. That's the only problem that we have here. And then to handle glue code, we again use template Haskell, where we assign our sort to, in this case, a placeholder, so in this case, all command types, with a function that we want to execute when this constraint is met. So in this case, we want to, when app's body is, or when command is part of the app's body, we want to run the app's glue return, which wraps our body into the handle return. This is to turn the abstractions into procedures. And this, in turn, gets generated by template Haskell into an instance over another type class. And this type class is defined over the a special glue type, the sort we want to target, and our semantic domain. This allows us to define multiple glue functions over different semantic domains without having to write our specialized or modified catamorphism every time. And then the getGlue instance is defined here, where we just have our operand, which is not used at runtime, but it's for type information. We have our term, and then we have our target, and we give a new target back. This allows us to transform the semantics of an already translated operator into a modified version, but we can't actually modify the operator we are modifying, which ensures some consistencies when applying glue code. So when you apply glue code, you can't just modify the operator you're gluing with completely. That goes against the idea of our system. So there are some constraints in there. And now I've used this template Haskell a lot. And why do we do that? It allows us to capture a language as just a simple data type in Haskell. So here we have the data language, which is our language data type. It contains out of operators, our assignments of operators to sorts, our subsort declarations, glue code, and our initialization code. And why is this useful? Well, first, let's see how it looks. This is how a language construct of our earlier introduced Lambda calculus looks. So first we define the auxiliary sort, which is done via the type family. Then we define our language, where we have our operators, our assignments, and our subsort declarations. And because we are just working in Haskell, we can just use Haskell. So here we just have list comprehension to make it a bit easier. And now, 5 minutes? Perfect. And now, the great thing about this is that we can just write functions over our data types. So we only actually need one function, which is the composition function, which is what we wanted to achieve. So we have a composition function that takes two languages and then returns a language. It just does a union on the operators, a union on the assignments, a union on the subsorts, and it does function composition on the glue code and the initialization code to turn it into a new language. And then, what can we achieve this? Well, here are a couple of examples. We have, we import here the Lambda language that we just defined, and we import the expression for that. This creates a dependency of our current language on the existing language. So dependencies are handled via Haskell. Then we define the arithmetic language, which has two operators, addition and integers. We then assign these operators to the expression sort, which we inherited from the Lambda language, where that dependency is, and then we assign this expression over our language. So what this does is it adds integer addition to the Lambda calculus, and it allows us to use integers inside lambdas, inside Lambda bodies, and lambdas inside integer, inside addition. And now we can compose these two languages together with our composition operator, and we get out of it the language that supports both Lambda calculus and integer addition. But we now have here a dependency. What we can also do is we can do unification, where we don't have a dependency. Instead, we have now 3 items, so we do double composition of languages, where we have our Lambda language, we have our arithmetic language, and then we have a glue language, in which we glue the two languages together. This basically does the same thing, where we assign the sorts to an auxiliary sort and then combine them together, but in this time we don't have a complex dependency. You can even take this one step further, where you define higher order languages, which take a constraint, which take a sort, and then define the language in terms of that sort. This way you don't create a concrete dependency, instead you create an abstract dependency, which is also nice, and then you can play a bit around with that. And lastly, we also have restriction. So in this case, we have the Lambda language with the arithmetic language, and we have a modified exception language. So we have some exception language that implements exceptions, so we can throw and catch them. And then in this case, we want to remove the catching so that we can only throw, and an exception is an error we can catch. So what we do is we just simply write Haskell functions. We just write a function over our language that removes catch from our assignments, from our operators, and remove catch from our sorts. And this way we have a modified language, and then we can compose this together again. And this is restriction. So now we have extension, unification, and restriction via our composition operator, which corresponds to the operations used by Erdweg in a survey on language composition. And these were the 3 operators he introduced, and we support all. And now that we have composition, we also get the incremental aspect for free, because we achieved the composition. And then the conclusion of our investigation is that the approach is highly flexible. We can create a lot of variations by simply changing the structure of a language, and we don't have to introduce new operators or change or duplicate a lot of operator code, etc. We can do rapid prototyping by just changing a sort declaration and seeing how that affects the language. So for example, if you have nested functions and you remove that sort declaration, you suddenly have a language without nested functions. What is the effect of these changes on how you use a language, etc. However, it's sometimes difficult to track how composition affects a language, especially when you have glue code. You might have multiple compositions, and these compositions can all apply glue code. And then you suddenly have composition of glue code, and how does this exactly relate to the effects on your language? I mean, you have a lot of operators, a lot of languages that you compose together. This might get a bit complex. So we need to find a way to make that clearer to the user. And our implementation is nice because a lot of properties are checked by Haskell, so it ensures that every operator has a translation to the semantic domain. It ensures that you don't use operators in the wrong place where you shouldn't use them, etc. But the interactivity is hampered by template Haskell. So because of template Haskell, we can't currently work in the REPL. We have to go back, compile, and then restart the REPL again. And as you've seen, the language definitions can be a bit verbose, so that's not great. So in future work, we want to develop an external DSL to utilize the interactivity aspect that we get from the composition fully. And our current implementation can function as a foundation for that, because we can base it on the same idea of functors, co-product of functors, and catamorphisms over these co-products. So that's nice. And then we also want to figure out how to handle user-defined concrete syntax. I'm currently only talking about abstract syntax and the translation to the semantic domain, but how can we handle concrete syntax? It's also something we will explore, and other algebras. We now have a translation to the semantic domain of Funcons, but maybe there's possible translation to a type system or to scope graphs to add support for the language server protocol, etc. So there's a lot of work to do still. But the main conclusion is that we can now support incremental language definition via composition, and we don't use flexibility or duplicate operator declarations. Thank you for your attention.
Thank you very much. That was abstract. I'm stunned, personally. Before we proceed to questions, there is an announcement. We have a voting system, which I think you are all familiar with. Because you probably want to stay here, we are not collecting answers at the door. Instead, this guy is going to go around the house handing you the tablet so that you have a chance to press the green button with a smiley face, meaning that you loved this talk. So go. The audience is yours. And questions, please. Or are you stunned as well? Ladies and gentlemen, we are not done yet. I'm sorry to say that, but there is a question to be asked, and there will probably an interesting answer coming soon.
Yeah, so I think on the second slide you mentioned, I mean, there was something mentioned like principled approach to REPL.
Yes.
And can you like give an intuition? Because I got the principled part in this talk, but I'm not sure if I can see how this relates to REPL. So could you give an intuition?
So the idea is that if you have the composition of two programs, if you can compose any two programs to form a new program, and the interpretation of the composition is the same as the interpretation of the two programs in isolation, then you get the incremental aspect for free. So you basically get REPLs for free. So if your system satisfies these conditions, you get a REPL for free. So you don't have to implement you don't have to implement a REPL. You can just pass it to a function, and if it satisfies these conditions, you can just get the REPL for free. So if you have composition of programs and you satisfy this diagram, you can basically give your language to a function which does the REPL stuff for you. So the idea is to minimize the language engineer's work.